Alrighty, so today, minerals. Giving this lecture in geology class, but sometimes other classes hear it as well. Earth science, for example, will hear this lecture, and you guys have slightly different requirements than the geology folks do when it comes to minerals in the lab. All right, these folks on campus have slightly different requirements than even the folks online do. Folks online, we look at a virtual mineral gallery for the most part. And you folks at, and they also have a specimen gallery, all right, or not a gallery, a specimen box. You folks in earth science have the specimen box as well. So some of the stuff I talk about might not apply to all of you. Just my little disclaimer there. I'll try to point out when it does and doesn't, but if you ever have questions, please feel free to ask. But everybody at some point in the semester in lecture class is responsible for some knowledge about minerals. And we're going to begin that conversation today. And bless you, by the way. So minerals and elements. All right, this goes back to, again, yet another reason why we talked about the atomic review stuff. You guys aren't going to be regurgitating formulas for me in lab. You saw that we don't even really are. You guys never have to come up with the formulas then either. We use them for the mineral groups, okay? But I never have you regurgitate a formula for me or anything like that. So again, it's just to give us a little bit of background to hopefully one less thing for you to get hung up on when we're talking about all this. So what is a mineral, dang it? Well, a mineral is something that's composed of one or more elements, all right? And they are things that we've divided into two different categories based on that first bullet there. We can say that they're going to be compounds, which are things made up of multiple elements, right? Or they are in a group called elementals. Now, the on-campus folks in lab, we've had this conversation already. You folks online for geology, you're just starting this week. Okay, so as to whether or not you've done this or not is entirely up to whether or not you started lab yesterday, Wednesday. All right. You're familiar then that, or what you'll come to see as we talk about this, is that the majority of those mineral groups are compound groups, you guys. All right, just the one group called elemental, of course, is an elemental. All right, talking myself into a corner there. Minerals are composed of elements, all right? Luckily for you guys, if this were a class, let's say for majors or whatever, even then, you probably wouldn't be responsible for the formulas that much. But luckily for you guys, out of all of those 100 and some odd elements on the periodic table, there's only a handful that show up over and over and over again. We see there's like a top 8, okay? And in that top 8, there's 2 that are kind of like the flour and sugar of making minerals. They're in everything. Okay, they're those fundamental baking ingredients. Those are oxygen and silicon. You're going to come across the mineral group called the silicates. Those are the primary components of silicates. So when you see that oxygen and silicon combined account for nearly 3/4, 75% of the composition of the crust, makes sense why you saw so many dang silicates in lab. So here's that list. There's nothing really super strange in here. There are some weird elements out there, but as you know, they're not in this list. We got oxygen, we got silicon, aluminum, iron, calcium, sodium, potassium, magnesium, And if you don't round, which is hard to do for a geologist, but if you don't round, that leaves 1.5% of everything else. Now, yeah, if you know about the periodic table, you know there's a handful of things that are only visible for a fraction of a second in a vacuum tube at a certain temperature and so on and so forth. Periodic table gets kind of funky towards the end. But the majority of that table, and stuff you've known, heard about, and even just think of some, for lack of a better word, fairly common stuff, gold, silver, platinum, all right? And you know that those are rare, they're precious. Well, they are just one fraction of that 1.5%. So that's why there's not a whole lot out there. Again, you don't need to worry about this list except for the top 2 ingredients. Funny thing about this, if you go through and you do look at the formulas for the minerals you learn in lab, you're going to see some of these. But there's a handful of other things that pop up as well, too. You would expect, I would have expected, that, just these guys are there. It's close, don't get me wrong. It's close. Oxygen and silicon. You're going to be sick of hearing about oxygen and silicon by the time we're done. Oxygen and silicon go on to form the most common mineral group, the silicates. By the way, which one was number 1? I didn't belabor the point a moment ago, but did you guys note in your notes? Told you it was super important. Yeah, oxygen. So the guy that's not number 1 in the atmosphere, where you'd think you'd want it, right, is actually number 1 in the crust of the earth. It's kind of a little weird. It's not like free oxygen gas, the kind we were talking about, wanting to breathe and so on and so forth. It's bonded onto various other things like iron, okay, and silicon. So it's not free breathable oxygen. Please don't be confused about that. But just kind of neat there that it is such a high concentration in the earth itself. Now, and again, please, for those of you that still aren't printing these things out and are frantically trying to write everything down on the slide, don't write this. This is mostly narrative here. Okay. When we said that a mineral is composed of 1 or more elements, that's not the definition, the capital V. All right. It is a true statement, don't get me wrong, but it is not how we want you to learn it, to remember it, to be able to write it on the test. And even though I say this every semester, there's a handful of students who, at the very end of the test, when we get to that 4-point question, define a mineral, one of the few times you actually have to write out something for a test in this class. And I say, please don't write a mineral is composed of 1 or more elements. There's always a handful of people, out of perhaps desperation, who write a mineral is composed of 1 or more elements. Or they Google it when they're at home taking this test online. Don't Google stuff. I can tell when you're Googling it. Please don't write that down. It is important. It is the fundamental truth. But it ain't the definition. Now, that being said, I don't care how you remember this definition. If bullet points are your thing, Godspeed. Here they are. A mineral is naturally occurring. A mineral is inorganic. A mineral is crystalline. A mineral is composed of 1 or more. A mineral is composed of a fixed set of chemical or physical properties. You can just do that. I don't need all the extra words. I'll show you an actual, sentence structure in a minute. And don't worry, we'll talk about what each of these means. So if you like bullet points, This is what I want. This is why it's worth 4 points. There's 4 things. I'm going to switch slides. You'll see all 4 of these in the sentence version. So a mineral is these 4 things. Or a mineral is, if you like narrative, a mineral is a naturally occurring inorganic substance with a crystalline structure and a fixed set of chemical and physical properties. All right? Whichever one flows for you. They say the same thing. We're also going to have the definition of rock a little later in the semester. Same idea. The second time, you're going to have to write something down on the test, short of just coloring in or circling an A or a B or a C. Take the time to remember this. And again, I do prefer that you use the one that we're giving here. Okay? Don't go and memorize something that you found and, on the Google or so on and so forth. And again, if you're taking this at home, you're supposed to not use your notes or a computer or a friend, but if you're going to cheat, at least cheat off of the handouts that I give you and write down the definition from in class. So what do these things mean? Naturally occurring. Well, at the risk of being redundant, that means it occurs naturally in nature. It's not man-made, woman-made, squirrel-made, whatever. It just is. And that sounds kind of odd, but, there are a handful of things that just are. Water, air, arguably rocks, so on and so forth. You could sit philosophically after a handful of beers on a Friday night and argue that everything's a product of something, I suppose, but we do need to draw the line somewhere. This naturally occurring is leading up to is sort of a precursor rule to the second one, which is inorganic. It can still be natural, but be inorganic. Organic implies, again in this case, not something that's healthy for you or so on and so forth, what it's come to represent today, but a byproduct of life, okay, or life itself. Prefix in, just as a reminder, means not, very similar to a. We don't say aorganic, we say inorganic, but we do say abiotic. I don't know why. But they use these prefixes, I suppose back in Latin or whatever, it sounded better then. Or those showed up as we translated from Latin and Greek. Who knows? I'm sure somebody knows. But now, this is the big twisting point here for when we move on to rocks. Some rocks will be organic, but no minerals are. And a lot of people get confused here as well because they're thinking coal, and you always hear about coal with mineral this and mineral rights that, and of course we mine minerals and so on and so forth. Coal is a rock, and it is organic. So arguably not a mineral for that reason. So naturally occurring, inorganic, crystalline. All solids are crystalline. All right. There's a few exceptions to that rule. You guys are sitting within 10 feet of one exception to that rule. But generally speaking, all solids are crystalline. What exception to that rule is there that you're sitting 5 to 10 feet from? Yeah, glass. Glass is non-crystalline. But we're going to ignore the exceptions, right? So we could learn the rule. When you think of crystals, again, feel free if you have this background in your head. But for me, Legos are perfect, okay? Just picture everything we're talking about being made out of little Legos. In fact, I use the Lego thing a lot. It works well. You probably heard me use it when this semester we had the recording of the atomic review that you guys had to listen to. But in lecture, I usually use that. We talk about the smallest little pieces part of a Lego, and we move up from there. So, think of Legos as crystals, and in such that not only do you build things out of them, but the shape of those Legos has a whole lot to say about the end product. Okay? Now, not all crystals are cubic. There's a crystal for every three-dimensional geometric form that you are aware of, and then some. Okay? Crystals come in all shapes and sizes, but all shapes. And when you put them together, they can't help but have some effect on the end product, as we said, the mineral itself. Again, if this were a class for majors, we would spend a good amount of time talking about the importance of crystallography. All right. As it is, however, it's just one small part of this semester. But out of homage to that, we will talk about in depth a little later today the most frequently occurring crystal and the role that it plays in making your favorite or soon-to-be favorite mineral group, the silicates. So we still talk about it, just we limit it. We limit it. Fixed properties. Fixed as in unchanging. All right? Chemical and physical. The chemistry makes the physical. It took me a long time to I don't want to say fully accept that, but to realize how important it was. All right? As much as I hate to begrudge to the chemistry teachers here and so on and so forth, arguably they could have a good fight with physics people, but chemistry underlies everything. Physics holds it together, maybe, so again, they might have a good point. Depends who's better at arm wrestling, I suppose. But everything is because of chemistry. You are you, your cat is your cat, your dog, that tree is the tree, because of its chemistry. And that makes the physical. Huh? Okay. I don't know about the not separating. We're actually going to talk about those, though, in a couple minutes. Oh, no, we talked about those when we did compounds. We talked about those. It's one of my favorite ones. Poisonous gas and a flammable solid make French fries taste better. I just love that compound. But at any rate, so, I see why it's up here on the slide. Sodium and chlorine, okay. These minerals are what they are because of their properties. And that's why, okay, we could use these properties in lab like we did to identify them. We could set down these tables, create these tables. Now, as you guys saw, as we're going through the process, it isn't perfect. There were times, even though we said, these are unchanging properties, you're like, yeah, sometimes the hardness isn't right. It happens. All right, but again, generally speaking, and what you also have to remember, and I tried to get this point through to you guys early on, is science is our attempts at understanding nature. She does not have to obey our tables. Our tables are our attempts at classifying and categorizing and understanding her. So when something falls out of the table, out of the realm of a table, that's as it should be, I suppose. Our tables point to the general. Okay? If you've used one of those tables for identifying trees, maybe, whether you were in another class or in scouts of some sort or whatever. Okay? Not everything fits nice and neat into those tables. Most everything does, and that's why it's so nice. So, at any rate, the underlying chemistry doesn't change. Salt is always made out of sodium and chlorine, as the example I gave, so on and so forth. And because of that, now what can be hard to believe is that all those properties that you learned about salt came from the simple fact that we're just mixing two things together. That I could, I agree. But now things like color, again, that's an odd one. You've seen Himalayan sea salt. We have a jar of it on our counter that's pink. Okay, there's blue salt out there. There's gray salt out there. I know color's in our list of things, but there's impurities and so on and so forth out there in the world. Okay. You can still make chocolate chip cookies, but with that little twist that makes them, just like your grandma used to make it. Now you'll be famous for making, and so on and so forth. They're still arguably a chocolate chip cookie. Everyone will recognize it as a chocolate chip cookie, but it's got a little something special about it. That's the level of properties we're talking about here. Yeah, and this is just, again, more narrative, but this is kind of what I said. The physical properties are unchanging because the chemical properties are unchanging. All right, so, again, definition of a mineral has 4 parts: naturally occurring, inorganic, crystalline, fixed set of chemical and physical properties. Yes, it is true that a mineral is made up of one or more elements, but that is not the definition. It's just something we needed to start with to sort of explain these properties that we put so much, these classifications that we put so much emphasis on, at least in lab. So speaking of which, classifying minerals. So we recognize 6 main mineral groups. For the folks sitting in front of me, we just did this yesterday in lab. Oops. But for you folks at home, you haven't had this conversation yet, more than likely. So we're going to go into it like I haven't talked to these guys about it. So the 6 groups we recognize are the silicates, the carbonates, the elementals, the halides, the sulfurs, and the oxides. All right. And each of these, as I hinted at earlier, are classified based on their chemistry. There's a whole lot of ways to classify minerals. Some arguably more practical than this, but as this is a college level course and a fundamental, basic geology class, we're going down to the most fundamental aspect of it, their makeup. All right. So we're using stuff based on their chemistry. If you bought a mineral guide and rock guide from Barnes & Nobles, for example, or something like that, you might see some of these show up under different groups. Ores, O-R-E-S, is one that they love to use. And again, that's fairly useful. Sorry, I put too big of a bite of my scone in my mouth. An ore is anything that is mined or dug up. Okay? Well, I'm getting ahead of myself. I'll show you the examples when we get there of why that doesn't work for us. I know how to turn this off where you click one at a time. It doesn't work on this PowerPoint for some reason. It's so old that it somehow has lost its ability to click it off. So every so often I'll click through to the next slide. So the silicates. What is the 7th time now you're hearing this? Most commonly occurring mineral group. And it consists of minerals made with the compound we know as silica, which is SiO4. How many silicons are in that compound? SiO4, folks. How many silicons are in there? 1. How many oxygens? 4. Good. That is the extent of the chemistry knowledge you'll need. Okay? What if there was a bracket? Well, there is a bracket around it, but what if around that bracket, it would be a slightly different shaped bracket, there was a number 2? What would that mean? Okay. Yeah, there's 2 of those compounds, 2 of those molecules. We're not going to use that word. There you go. Chemistry scares people. I've been told geology scares people, but that's possibly if they know enough about it, they realize that it's all the sciences. People go into it's easy, I can do it. It's just rock, or it's this, just that. But geology uses all of everything. It's crazy. Carbonates consist of minerals containing the compound carbonate, which is CO3. So again, we've got one carbon and 3 oxygens. There are 2 subtypes of carbonates out there. The calcium carbonates and the magnesium carbonates. You guys only see one of these. You guys end up seeing calcite. Dolomite is cool. Dolomite is actually kind of funky. Last I heard, they were still arguing whether or not dolomite was even still being created. Calcite forms primarily in a marine environment, salt water. And they were thinking that, and again, I just haven't kept up on this, the dolomite only formed like in super cold marine environments. And I don't know where that argument ever went, but, or possibly nowhere. But there's not a whole lot of diversity. There's some other ones. There's aragonite. Aragonite's important because that's what a lot of fossils are actually made of. But in earth science and even in my classes, we just still call it calcite. But it's a certain special kind of calcite. But nowhere near like the silicates. And that's kind of misleading because calcite makes limestone. And limestone is absolutely everywhere. Oh my gosh, limestone. Limestone is anywhere and everywhere that an ocean has been. All right, which is at this point, yes, damn near everywhere. So by volume, and diversity, silicates still win. But there are. Do not let this fool you that there's only 2 types of carbonates. They're huge. Okay, they're huge. A huge group. This is arguably your easiest one. The elementals. The elementals are called that because they're made up of a single element. What's sulfur made up of? Sulfur. Copper's made up of copper. Graphite, carbon. Yeah, that confuses you guys sometimes. But, yep, graphite is just carbon. And carbon does a lot of stuff. Carbon's pretty unique. There are, and it's in everything, yeah. So this is a pretty straightforward one for you guys. The halides, dang it. The halides refer to a column on the periodic table, a group on the periodic table. All the way over to the right, you probably recall the noble gases. They like to make a big deal about that in elementary or middle school. All right, noble gases are cool. They've got their reasons. The column just before that, columns are vertical, by the way. Rows are horizontal, columns vertical. Just in case, telling you. Is known as the halide group. And as I like to say, it's got a lot of things that end in "ene" in it. Chlorine, fluorine, bromine, iodine, so on and so forth. That's how you're going to remember them. You have 2 halides that you see in lab. You've got halite and you've got fluorite. All right, halite is in the halide group because of chlorine over there. And fluorite is in there because of fluorine. All right, and it's not Fl. I still make that mistake myself. It's just F. So if you found a mineral, let's say we had an unknown or something like that, you did manage to figure out its formula, and you see that it has bromine in it for some reason. I don't know what we'd make to have bromine in it, but something with bromine in it. It would be classified again as a halide. The sulfur groups. I am going to, not rant exactly, but grumble about all these artificial groups I don't want you to use in a couple minutes here. But this is one we do want you to use. As I said in lab yesterday, there's sulfates and sulfites. If this were a place where we had a lot of majors, we would talk about that. It's about how many oxygens are bonded into the formula, and there's lots of neat reasons why that exists. At this point, and again, it's not just me, there's many other Geology 100 level classes that do this same idea. We're not going to fuss about how many oxygens in the formula. We don't give a rat's behind, okay? Just happy that you recognize that. Capital letter S is a sulfur. And when you come across sphalerite or galena or pyrite, and you're writing down the formulas that you say, oh, hey, that has sulfur in it. That must be a sulfur group. Because you've got a lot of hard ones out there. So it's nice to have a few easy ones. So the sulfurs. And again, you folks at home primarily on this one. If I see sulfates or sulfites on the mineral practical, I'm going to ask you why it's a sulfate or a sulfite and not the other one. If you can't answer that, I'm going to mark it wrong. Please use our groups, not the ones Google tells you about. The oxides. Probably the last bullet point, but I'm going to get bold. Yep, I knew it. I should have stopped. All right. The oxides. These are the oxidized minerals. Duh. But how do you tell if they've been oxidized? Sometimes it's not quite so simple as they've rusted. Again, rust being only one type of oxidation, I'm obliged to tell you that, which you may call tarnishing. Okay, silver tarnishes. What copper does, turning to green. Those are all types of oxidation. Okay. Generally speaking, we only say rust when we're talking about these iron-based steel rusts. Okay, iron oxide is rust. So oxygen's been added to the chemical makeup, but that is oftentimes hard to tell. Not even just at this level, but someone in arguably in a junior or senior level class, if they're not that familiar with this stuff, it's hard to tell whether or not that oxygen was bonded there deep down inside the earth, or if it came later from exposure to the atmosphere, for example. So again, at this point, we don't worry too much about that. And we tell you that, guess what? It's your rusty specimens in lab, aka 14 through 17. But there are way more out there than that, of course. So those are the 6 groups that all 32, 31, I forget how many minerals we end up looking at in geology. In earth science, you guys only get 4 or 5, half a dozen roughly. All right. So you get off easy, and you don't have a mineral practical either. But in geology, we've got a mineral practical, and the groups are 1/2 of that test. Not only do you have to say that's sulfur, but you have to tell me it's an elemental. That's rose quartz, it's a silicate, that's galena, it's a sulfur, and so on and so forth. So the groups are very important in lab. In lecture, they end up accounting for a couple test questions, really. So, these artificial groupings. That one shows up all at once. Gemstones. That's a big one. But boy, is that vague. Anything from amethyst to a diamond could show up in gemstones. Why does that matter? Well, amethyst is just purple quartz. Diamond is, well, just carbon, but it certainly has a different value attached to it. And everything in between. So it's kind of vague. Ores, as I started to talk about a little bit ago. Ores are anything that is mined, right? What do we mine? Well, we mine diamonds, we mine gold, we mine silver, we mine salt. And I think I picked enough examples there. Each one of those things has a much more specific category that we could use about it. Salt was a halide. Diamonds and gold and silver are elementals. I guess I didn't pick any other group, but it's a lot of stuff. Almost all of this stuff is dug up. So ores is sort of a trade category. Okay. It's great for Congress people to be able to talk about using just a collective term. But you see it in these books. You see gemstones in these books. So, and it's not that I don't want you to go buy these books. They're awesome things. They're nice to have. They look pretty on your shelf and so on and so forth. But when it comes to the test, all right, stick to what we're talking about. And then, of course, there's the software group, which we encourage you to use. So, but I explained why we use it, so on and so forth. All right. So, that wraps up the general conversation. From here, we're going to take an in-depth dive into the silicates. Why the silicates? Because we can talk about all the important things we need to pay tribute to and illustrate their importance in something that will really, kind of cover 3/4 of what you guys run into. So that's kind of nice too. There are other types of crystal structures out there. There are obviously other mineral groups out there, but we're focusing on one of them. Why? Because it's the most commonly occurring group on the face of the earth. If you don't see that as a test question, I don't know what you will see. SiO4, silica. So what is silica? All right, so silica is a compound made up of silicon and oxygen. I hope at this point you're like, yeah. Also, we talked about this already. There's 4 oxygen atoms around 1 silicon atom. How do we know that? SiO4, right? Now, what you did not know is their organization. The silica compound is in the shape of something called a tetrahedron. I use the word pyramid to refer to it because that is something that you can very easily picture. All right? A tetrahedron in free atomic space is something roughly, pick that pyramid up and put it on one of its edges instead of its corners. That's sort of the tetrahedral shape. It's not really bothered by gravity. It can do that. And generally speaking, there's a lot of other tetrahedra around it. They support each other, so on and so forth. The other image I like to give you, you can't completely do it, but picture your debit card or your student ID or whatever, and put it in your hands. Put your thumb and pointer finger on 2 sets of corners. Put your thumb and other pointer finger on the other 2 sets of corners. And imagine if you could twist it like halfway around one side of it, the top or the bottom, while leaving the other one fixed. And you get those 2 corners now facing, 2 sets of corners facing opposite directions. It's a little hard to visualize this early in the morning. And again, you can't really do that without breaking your card, but if you could. So that's the shape we're going for here. And again, why we just talk about pyramids. So here is said thing. You see how we have 2 corners going left to right, 2 corners going front to back. I've been here 22 years. I was other places probably 3 years before that. So for 25 years, I've been thinking, boy, I really ought to glue 3 racquetballs together. I haven't done it in 25 years. My kids laugh, and your parents probably say similar to you. Oh, I remember when you... 5-10 years to us is way different than 5-10 years to you guys. I can actually say I've got stuff I've been meaning to do longer than you've been alive. And it's more than just glue 3 racquetballs together. But at any rate, so another way to picture this is if you play pool. Some of you may not know what a racquetball is. Pretty much everybody knows what a pool ball is, though. You got 3 pool balls to make a triangle, right? Set one on top. Now, of course, we live in a world of gravity and other physics rules. That would roll away, it would fall apart. But imagine for a moment if it didn't. Okay? That's that pyramidal shape. It's still 4 balls, but because of the world we live in, it's organized flat on a table here. That's why we can call it a pyramid. In reality, lift up one of those corners, and you got your pyramid on its end. I just want to make sure we're all in the same area here. Now, imagine if you could take one of those balls away and place a small, I used to call them super balls when I was a kid. They used to be a dime. The tiny little bouncy balls. For a while, I think when you guys were kids, they showed up in the heels of your shoes to give you extra spring in your step. Like a 10-year-old needs more spring in their step. But regardless, those tiny little super balls. Okay? I think by that point, they were 25 to 50 cents when I was buying them for my kid. But the little bouncy rubber balls. Drop one of those in the center of those 3 balls and then put that 4th ball back on top. Again, you can't really do that in our reality, but that's the idea here. You see that pink ball in the center there? That's our super ball. These blue balls are the oxygen. The pink ball is the silicon. SiO4. How many silicons do we see? 1. How many oxygens do we see? 4. Good. Just out of curiosity, what's the most commonly occurring element in the Earth's crust? Oxygen. Do not get that question wrong if you got this one right. 4 times as many oxygen in this molecule as there is silicon. Remember that. Now, I don't think that played out in the percentages, but I think it was like, I'm not going to try to guess, but it wasn't 4 times. But the point is there's way more oxygen in here than there is silicon. Okay? So when you're asked about the top 2 ingredients, put oxygen first. Silicon oxygen tetrahedron. Tetrahedron is the shape. Tetra means 4. That also maybe will help you. And tetris. Yeah, all of this, they all made up of 4 blocks?
It's more if you break 4 rows at once. That's
yeah, but I'm wondering the square, the strip. I'm trying to remember if it's 5 or 4, especially the L. And I can't remember if the L is.
They're all 4 blocks.
I think it's all 4 again. Actually, that's a good. That was a good buy. We watched that on Netflix or something. The story behind Tetris. If you guys are ever really bored one night, it's a great.
The guy who made it.
Well, yes, but they made a good biopic, for lack of a better word, out of it. It's worth an hour and a half of your time. What?
They're all 4.
Huh?
They're all
4. Okay. Thank you.
All 4, and if you
break 4, it's a special bonus if you get 4 in a row?
Yep.
I hardly ever get to do that, but.
That's when the game will announce that you just did Tetris.
Oh, you Tetrised.
Might be the greatest game ever made.
It is. I grew up in the era when that was on the Game Boys. So that was a big time killer. I mean, I grew up with Mario, but.
It doesn't matter who you are. You kind of just like playing Tetris.
It's a good game. It's a good game. All right. Did I even change slides? I think I did change slides. Oh, I didn't change slides. I just added stuff. So a tetrahedron resembles a pyramid. We said that. So a silica crystal is a silicon oxygen tetrahedron. Just to make that clear, okay? One silica crystal is in the shape of a tetrahedron. Now you're thinking, wait a minute, we just listed 12 things yesterday easily as silicates. And you told me that the crystal shape helps the outcome of that mineral. The quartz didn't look anything like biotite mica, which didn't look anything like orthoclase feldspar. What the hell are you talking about? Well, unfortunately, that's where we're headed with this. All right. The way you could arrange these tetrahedra will change things dramatically. Not just in the outcome and the shape, but in the durability of said structure as well. I just sort of said that. So you had a bunch of different ingredients in those formulas. Sometimes the formula was as simple as SiO. Please don't ask me what happened to the other 3 O's. I don't know. Actually, I think it was SiO2, but still. That is above my pay grade, as they say. But sometimes just as simple as silicon and oxygen, and sometimes as simple as there's 6 more things in there. Hydroxylated aluminosilicate. Blah, 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 blah. I did take mineralogy, I just didn't enjoy it. But don't let me dissuade you guys from enjoying the heck out of this chapter. Surface processes and critters. Minerals, yeah. And speaking of which, by the way, not that, but what I said before that, this is the first time we're finally chapter-based, okay? If you're a chapter reader, your time has come. There is a minerals chapter. Please read it, okay? I've excerpted, I've distilled, okay, the important stuff that we need to get through to the next, bits of information and so on and so forth. But yes, we finally have a chapter. This PowerPoint is from a chapter. What chapter number it is? 3 or 4, I think. And yes, the table of contents will guide you there. But, all right. So about all that other riffraff. Believe it or not, it's the rest of that list of 8, which I still don't need you to memorize. But it should go without saying that if you've got 8 most commonly occurring ingredients, and we're talking about the most commonly occurring mineral group, that there ought to be some similarities. And this is what I started to chatter about earlier. You see these things, but there's also a little bit more thrown in. Well, the top 2, silicon and oxygen, we removed. Yeah. Yeah. The remaining 6. I didn't put that in, the remaining, but I said the word remaining, I thought. That might have been before you got here with the list of 8. All right. Nice. Yeah, I think there was a bit of an ice storm.
Yeah. A lot of my trees up on my hill are sagging because they've got a lot of frost on them right now.
But soon it'll be a one-tree hill. I think that was a TV show.
I think it is a TV show.
Still is. Okay. All right. Well, hopefully your trees are safe and sound. So, silica. More about silica. All right, worth pointing out. Silicon, silica, silicates. 3 very similar words. Silicon is the element. Silica is the compound. Silicates is the group. I don't have a question like that, but just, So, 4 oxygen atoms surrounding 1 silicon atom in a pyramidal shape called a tetrahedron. That looks familiar. Now, as I said, muscovite mica, rose quartz, labradorite feldspar, augite. Those are all silicates. But they don't look anything like each other. How come? Well, even this doesn't fully explain it, but this is part of the reason. All right, the way we put those little Lego bits together helps define what you see in the end. There's 4 main ways to do that. We call those silicate structures. There's the isolated silicate structure, chain structures, sheet structures, and framework. We're going to talk about and give you examples of each. All right, forgive my primitive drawings. That's pyramid-ish. All right, it is meant to be our tetrahedron, though. But again, I wanted to make the corners accessible for future drawings. So an isolated structure, single tetrahedra, are bonded together by positively charged elements. What does that mean? Well, let's look at olivine. Remember olivine? All right. You folks at home, you won't have the pleasure of having olivine in your hands. Imagine a sandy green rock. And when you rub said sandy green rock, you get lots of little green crystals in your hand rather easily. When they dragged a nail across it, it totally crumbled, right? But you don't even have to drag a nail across it. If you rub it hard enough, you're going to get some crystals falling off in your hand. So, first point of matter. This doesn't mean that we're looking at one crystal. Okay? And arguably, each one of those little grains of sugar or sand isn't necessarily one crystal, but we're going to pretend for a moment. All right? Those fall apart so easily because they're held together. Those individual crystals are held together by little more than static electricity. It's not static electricity, but the same idea. If you've rubbed a balloon on your head or a sweater and it sticks to somewhere, that's the static we're talking about. And that's what's holding those guys together. Olivine itself is very hard. But as we said in lab, you need to test the hardness of is one of those tiny little crystals, and that's really hard to do. So there's a whole bunch. There's hundreds, if not thousands, of little crystals in that, but we call that an isolated silicate because these corners aren't bonded to other corners. And that's where we're headed with this. If you know anything about chemistry, these are oxygen bonds that we're building. Oxygen bonds are pretty good. Good stuff. Garnet does not display what we just talked about, but it is another example of the same thing. All right, you're not going to rub the garnet and get little pieces off in your hand, but the garnet crystals themselves are not really bonded to any other garnet crystals in that hunk of loveliness that you had in lab. This one almost makes more sense in retrospect. Hey, I added pictures. I forgot I added pictures. So in the upper left-hand corner for you folks at home, this is your olivine. And in the lower right is garnet. All right, next we have chain structures. And chain structures actually have two types. We've got single chain and double chain. And these are exactly what you might picture if you imagine putting paper clips together. Daisy chain. I haven't seen people chain daisies together in a very long time. That's something little kids used to do and hippie chicks back before we had cell phones and whatnot. There's probably an app for that now. But the idea here is, what's at the corners again, by the way? No, those are tetrahedrons. What's at the corner of each tetrahedron? Or what does the corner represent in this case? Oxygens, all right? So again, oxygen to oxygen touching, that's an oxygen bond, that's wonderful stuff. That's your single chain. Your double chain is just that, two chains bonded together. We're using more oxygen bonds. Not only is it a little stronger, it is a little more prevalent. And why are two examples, augite and hornblende. You may remember these from lab. You may recognize these when you do get lab, you folks at home. That augite didn't really have a really well-defined crystal structure. It was there. That was the grainy black and green one we talked about. But the hornblende, we said, had those long needle-like crystals in it. I'd like to think that you could see those long needle-like crystals because it's a double chain. It's just twice as wide. Makes it arguably that much easier to see and structurally that much more prevalent. So again, augite in the upper left-hand corner, hornblende in the lower right-hand corner. This can be pretty. We see them in igneous rocks. They impart a nice contrast. Guess what? If you glue more than two chains together, We call them a sheet structure. You saw some sheet silicates yesterday. One of the first things you encountered was one of the micas. And we all played with the bendy nature of the micas and said, ooh, these look like sheets. Little did you know, right? Now, in lab, for those of you taking the rock test, in other words, not earth science folks, I do not require you to tell me it's a sheet silicate, it's an isolated silicate, it's a framework. We just call it a silicate, okay? In lecture, though, I do want you to remember some examples. And that's why I've given you, sparingly few. I think we've given you 2 examples of each one so far. You need to, remember one of those. Talc, by the time we got to the very end of the minerals pile. All right? Talc, if you didn't have one that was smudged into oblivion, you could still see the fact that there were layers in there. Little stair-step edges that kind of you could picture was a deck of cards at some point in time. Now, what's important, though, is how easily the micas peeled apart. Ideally, you didn't sit there and flake apart my micas, but you saw the pieces parts in the box when you went back to put the stuff away. That stuff peels apart, really easily. That's because those layers are held together, again, by little more than what held those olivine crystals together. It's not bonded top to bottom. That's the one thing that's still to come. So we have these sheets formed, and they're very strong across those sheets. You could take one of those tiny sheets and practically bend it in half, and it won't break between your 2 fingers. But peeling apart, super easy. There's some muscovite. All right, so what remains? Oh, I got rid of my animation. Oh, crud. A very crude animation. There's my mouse. I lost my mouse. So I used to have, and I really don't know what happened to it because I don't remember erasing it. I used to have a click built in where I could take off this top layer over here. And what I'm attempting to do here is line up the center of these pyramids over the tops of the pyramids below it. Now again, because these are tetrahedron, they're not actually shaped this way. It's kind of a, not really what's happening, but I'm trying to make a point. All right? And that point is that we're now taking the top of the pyramid below and bonding it to the bottom of the pyramid above. We've glued those sheets together, so to speak. We've used up as many oxygen molecules as there are, oxygen atoms as there are. And lo and behold, we've made some of the strongest silicates, the quartzes, the feldspars that you came across. There's got to be some connection there, right? All these oxygen bonds give us some of our most durable silicate structures. Now, your book is going to talk about the fact that there's some accessory elements in here. There are. I want to just keep it simple, and I wanted to build upon these structure ideas. There is slightly more going on behind the screen. Okay? But for all we care about right now, we've taken that last set of oxygens that were available, and we bonded them to the other sheets. Also interesting to note is that nearly 75% of the crust is composed of framework minerals. So we told you, if you recall, nearly 3/4 of the crust is silicates. Nearly 3/4 of those silicates are frameworks. So again, in my mind, that just goes to figure, okay, these are some of the most durable silicates out there. Just over time, they've stood the test of time. That's what's left. It's sort of, I don't know that it's always been that way. I'm approaching it from the angle is that it's grown to that percentage. But at any rate, 'tis what it is. And you'll see over and over again, when we get to igneous, you're going to see quartz and feldspar all over the place. All over the place. And then we don't point it out as much, but when we get to sedimentary rocks, which are parts of all those other rocks that are broken down, guess what the majority of your components in those are going to be? Again, quartzes and feldspars. So, they stood the test of time. Quartzes and feldspars. And that, my friends, is all that I felt was necessary for us to learn at this point from the mineral chapter. Again, I do encourage you to read it. There is some stuff that I have left out. If any of that stuff makes you uncomfortable, why didn't you talk about this? Feel free to ask me, okay? Or if you read stuff that we didn't talk about and you have questions, again, feel free to ask me. But with regards to the test, this is what will appear. All right? I'm not one of those teachers who takes your time up. I forget what we're on here? We're on 1 hour and 1 minute. Okay? Stand here for 60 minutes and talk about a whole bunch of stuff and then put 6 things that we didn't talk about on the test. I always hated those kind of teachers. My daughter just got done with one of those teachers in a history class. And it took me a while to figure out what he's doing. I'm like, oh, honey, you got to actually read this and so on and so forth. And that's fine. There is a method to that madness. I get it. But I don't do that. So if I didn't talk about it, you aren't going to see it on the test. Kabish? We good? Okay. And that goes for any chapter, really.